todo. Voy a hacer la presentación en inglés, si no es más fácil para mí. Okay, I'm very happy to be here. First, thank you all the people there to come, and also for inviting me. Actually, I am here for 1 month to accomplish a quite ambitious project, actually, for 1 month, but I think I will succeed. The idea is to use some numerical tools I designed many years ago, but now I have just released a new version, more efficient, of course. And the idea is to try to find a way to restore or to improve the quality of the sky in the Observatorio del Teide, actually, here. So how can we do that? If we are very ambitious, maybe we can hope to recover a sky as good as in La Palma. I'm not sure now, okay? We have to do the computation to do it. So today I will give you first some information about, light pollution, because I guess not everyone here know a lot about that. And after that I will talk more in depth about the model. And at the end, I will give you some insight about what I'm doing precisely here in La Laguna. So first of all, light pollution. What it is? I think you know, most of you know what it is, but I want to show you some images to illustrate the phenomenon. This is a very good sky, like we will maybe have in Tenerife in some years. And this is actually a sky that we can see in a small city, typically a couple of thousands of people. So you can see that we lose a lot of stars. There are two components to light pollution. The first one is what I call the direct light pollution. This light is coming from the light fixture, of course, and going to the ground. So this kind of pollution mostly affects, for example, the fauna and even the human people. And for astronomers, it is less important, of course. But the second part is what I call the indirect light pollution. And this one actually is going up, hitting some particles in the atmosphere and then go down to the observer. And if you look into that direction, of course, you will see the stars, but there's a kind of competition with the light pollution coming from the sky. This is an example of a place. We use the kind of tool I designed to restore the quality of the sky. It is an observatory in Canada. This place, after the project, we reduced to the half the level of light pollution. So it is possible to improve the thing. I don't know where, because it depends on a lot on the configuration of the cities and everything. So we have to calculate it, but I think we can improve it. We can see. Noise. Okay. Some word about the model. We call this model Illumina. Before 2 weeks from now, we were using version 1, but now it is the second version. 10 years between the two. And just for the funny thing, I released the first version here 10 years ago. So, so I think I have to come more often to Tenerife, maybe. So what is the model? Basically, there's some change between the two versions, but the basis is the same. It is a ray tracing algorithm. So we have to define, for example, the light fixture that are on the ground. Then from that light fixture, you have to know a lot of parameters. For example, the power of the lamp fixture, the spectrum, what we call the photometry, the way that the light is exiting the light fixture in terms of angular intensity. And then if you have all this information for each pixel of a given domain, geographical domain, then we can start throwing photons from there, okay? Of course, we have to define one very important thing is where is the observer and what is the observing angle. But when you have done that, then the photons are going out from the sources and all the computation is made to calculate what will be the sky radiance observed by this specific observer and position. And so it is of course a kind of statistical method to reduce the time because ray tracing algorithm can be very difficult for computers in terms of computation power. It is the new version that I just released is a multi-scale scheme. That means that we are modeling very precisely near the observer and then reducing the resolution as long as we go farther from the observer. And this is important because we find in the previous studies that the light that is the most efficient to destroy the night sky is the one that are very close to you. It's surprising because we don't feel it when we look to the sky. Okay? But it's a bit complex. You can understand that the photons are going away, but what we are looking at is the photons going down. So these photons can just start from this light fixture next to you, go up and go down to your eye. But you will not notice that it comes from there. This is the point. So this is why we need actually a model. A very important aspect is that we account for the hyperspectral characteristic of many things, including, of course, the sources, but also the way that the ground reflectance, because you know, big part of the light is coming from there. So we have to know what is the reflection as a function of the wavelength. And of course, the radiative transfer in the atmosphere is dependent also on the spectrum. We are calculating many things like shadows, given if, for example, you have a mountain between the observer and the sources. There's some calculation to account for that. And I will go faster maybe, but because there's a lot to say, but not so important. But we account for aerosols. The vertical profile is computed also, not only for aerosols, but molecules. And the kind of aerosol is important because, the composition, the chemical composition, but also the size distribution. Because the phase function, what we call the phase function is the way that the light will be redirected by the scattering, is highly dependent on the size distribution of aerosols. So to summarize that, there's a lot of input data to enter into the model. And this is the difficulty of this methodology actually. Because the question is, how will I succeed to find all these data and what will be the accuracy of the input data? So this is a big challenge actually. Okay. It's okay? Okay, thank you. Yeah, so this is a big challenge. I forgot to say that there's also a cloud scheme in the model, but this one is more dedicated to the people working, in biology, because the clouds are some kind of amplifier of the light pollution, but for astronomers, of course, when there are clouds, we are not observing. So this is less interesting for you. The thing that still remains to do in the model is to put low-level clouds, because you know, most of you know that there's often that kind of clouds here on the island. Now the model cannot do this kind of computation, unfortunately. It will happen maybe next time I will come, no? Okay. Let's talk about actually the typical input we put in the model. So first we have, as I said, the upward radiance. What we use actually is a satellite. VERSE DNB is a satellite platform that observes the Earth at night. So we can, with that kind of data, we obtain finally the light coming to the satellite to space. But this is not exactly what we need. What we need is the light at every angle. Okay, so we are doing some complex computation, knowing this parameter, this information, but also what is the reflectance of the ground. Okay, knowing these two parameters, we are able to estimate what is actually the light, the total light that went out from the from each light fixture. So this is the ID, and it is possible to do it actually. We need, of course, as I said, the ground reflectance, the topography, the aerosols. Actually, it's more the composition, but also one optical parameter, which is the aerosol optical depth, which is more or less the coefficient of absorption and scattering of aerosol. And relative humidity, which has an impact on the aerosol optical depth, and the ground air pressure. Of course, if you model, for example, very high altitude, you need to adjust the model with the ground pressure, because the density of the atmosphere will be different. And this is the hard part, actually. The angular light distribution of the light fixture is quite hard to get this kind of information, but in that case, in the present case here in Tenerife, I'm very happy to have an expert here. Javier helped me to try to find this information. Okay, up to now we don't have an automated method to extract this information, but we are working on that. Just a small point about that. I have a program with the Canadian Space Agency to observe the Earth's surface at night with stratospheric balloons. And the idea of that project is to do a flight over a city, for example, or a region, and we observe the same city at different angles as long as we go over the city. And with this kind of information, we will be able to replace this kind of marvelous expert we have here. But will it work? We'll see. Okay, and another very important point that is considered in the model is the obstacle. The obstacles are the small structures like buildings, trees, and we found in my research group that this kind of structures is very important to reduce light pollution. In some cases, it can reduce it by a factor of 5. Okay, so if you compare the same light fixture, the same ground, remove the buildings and put the buildings back, you will see 5 times less light pollution when the buildings are there. But it depends, of course, of the height of the light fixture relatively to the height of the buildings. Okay, so again, we have to find this kind of information. So I'm working on that now. I'm doing this with Google Street View to see in each zone that we identified in the island to see what is the typical height of the light and the buildings around. So not only the height, but also what we call the filling factor, because, you know, in a given place, you will have buildings, trees, but in some angles, you will have a free path for the light. No blocking at all. So we have to know that also, because the the buildings, the obstacles are not completely opaque. They are a bit transparent in a way because of that. So we need this information also. This is an example of the satellite image. Maybe you recognize the place. It is Hawaii, here Honolulu in that part, and some other island. This is maybe you know the Alaekala Observatory, the one who are working on exoplanets. Probably know that. And this is the big island. Actually, this point here, a very big source of light is the volcano. It's not really light pollution, but it has an impact on the sky brightness, of course. And this is the topography. We take it also from space data. I give the example for Hawaii because I don't yet have the results for here. So just to give you an idea. And then what we do is to combine a lot of data, as I said. So if we go inside this, we can see this kind of map. We have to identify some zones. Each zone will be characterized, will be estimated to have the same lamp parameters and obstacle parameters. It's an approximation, of course, but this is the best we can do now. So, but we can define, as you see, a complete island as a zone, but we can define also some smaller zone inside this big zone. So in each circle you can define different properties for the light and everything. Actually, this project was to check what happened in that observatory here. And the specific case is that they want to observe exoplanets and asteroids, and unfortunately, the main direction is pointing toward Honolulu. And there was a project to replace all Honolulu with white 4,000 Kelvin LEDs. And then the observatory was a bit anxious about that. And they asked me, is that possible to calculate something to protect our observatory? And I have done it. Actually, the zone 17 is for the volcano. So I have to define it also. Okay. So if you use the right equation, you can find this kind of data. I think I can zoom on it. Okay. This plot is actually the zenith angle here. So it represents the power of emission as a function of the zenithal angle from the light fixture, and on the other axis you have the wavelength. So for each zone we'll have some kind of data, okay? And this is what we need for the calculation in the model. Yeah. Going to the ground, actually. Yeah. Yeah. 0 is zenith. 90. Yeah. 0 is zenith. 90. 180. This is important because most of the light is going there, you know, and then it reflects to the sky. So we have to know all the angles. And this is the problem. This is the difficulty, actually, because what we see from the satellite is only this part, no? Only this part from the top. And there's no so much light in that direction. Okay. So this is the equation we designed to do the things. One problem we have, this is very important because, you know, with the new challenge with LEDs is that most LEDs, I think I will be able to show you a spectrum later on, but most LED have a very intense peak of light in the blue region. And this is a problem because the satellite cannot see that. And if we look to this plot here, this is the sensitivity of the satellite. But the LED peak falls right there. Okay, so if you look to the satellite images with time, you will have the impression that the light pollution is going down. But it's not the case because the satellite don't see more or less about half of the light from the LEDs. Okay, so we take it into account when we compute the thing because we have actually the curve, And we also have the curves, the spectral curves of the light. So we can correct this problem. So once you have all this data, you put it in the model. You need a supercomputer. I'm happy I have one, not to me, but I have access to a big one. And then we just throw it in the computer, and the calculation will be done. It is quite long because, you know, there may be, for example, multiple viewing angles. If you want to know all the sky, for example, there can be many sites. You can want to model different atmospheric profiles, for example, the level of aerosol that can change a lot the sky brightness. So this is why we need a supercomputer, actually, because one computation may take maybe 2-3 days, but typically with that kind of experiment, we are doing maybe more than 1,000 computations. So if you don't want to wait for 1 year for the result, you need a supercomputer to distribute the calculation. So this is what we are doing. And the typical output we get at the end is the first one is the most important maybe, but for the project is here not necessarily the most important, is the radiance. If you, for example, you define the observer at Observatorio del Teide, and you define the direction to zenith, then you will get the radiance at zenith. But not only one number, but the spectrum of the sky, okay? This is very important. And the other very interesting output we get is what we call the radiance contribution map. This is actually how from where the light is coming. What you observe in that direction is coming from what part of the territory. And actually it's like a percentage, okay, per pixel. So it is very important because with that kind of information you can know exactly, well, exactly not, but you can know with some degree of accuracy what are the most important source in terms of their contribution to the sky brightness. And then if you want to improve the sky, you can begin by these spots. Okay, this is the idea. So I will show you some results. These results were made for Alaikala Observatory in Hawaii. So this is an example of radiance output. So it's a spectrum. Actually, we have the wavelength, and here the sky radiance. And then in that case, we presented two zenith angles. The first one is 0, meaning this small curve there, meaning the zenith direction, and another near the horizon because they were observing the exoplanets more or less at this zenith angle. And you can see, of course, if you compare, okay, there's two cases also. The first one is what is actually now, what is the light pollution in that place. And we try to change all the light to put them to PC amber LEDs to see what will happen if we do that. This is a nice aspect of this kind of calculation. We can change the light before doing it really on the ground. No? So just if you look to the curves, this one is for the reality, and this is for all the light converted to PC amber, but at 70 degrees in that case, and this one is for the zenith. So you can see easily that converting to, in that case, note that most of the light were HPS before. So you can see that there's a huge reduction actually of the sky brightness. And the reason for that is that the light fixture now in Hawaii are very old light fixture. And you know some kind of prismatic lenses under, and that kind of lens can have 3, 4, 5% of light going up. And when you replace them with PC amber, most of the time there's no light going up. So this is why we have a so important reduction. And if you compute that kind of thing, but for all the direction in the sky, so now for that you need a supercomputer, then you can make some all-sky maps. And in that case, we have we took the spectrum and integrate them over the Johnson bands. And you can see here the V band and here the color index. So it can give you some insight about how the blue light or the color is distributed in the sky. So it can be very useful. Okay, this is actually not the good. I just realized that this is for another experiment in Italy. I made a mistake. Sorry for that. And going back to Hawaii. So this is the radiance contribution maps. So what, as I said before, the color, if you are high in the yellow part or white part, that means that these sources were contributing a lot to the sky radiance that was observed. And here the observatory is more or less there. So what was the conclusion of this experiment is that if we want to control the light pollution, the most important is just checking for the nearby cities. I mean nearby by a few kilometers away. So Honolulu is there, but you can see that it is contributing to the sky, but not so much. So it was a good news for the people there, because they were afraid with Honolulu, but it was not so important finally. But this is the current situation. We try, I don't have the plot here, but we try also to replace everything with white LEDs at 4,000 Kelvin. And we found that only a small part, it was of course an increase, but not a big one, a part of 1% of increase. So it was not a very big problem for this observatory. And we tried also to calculate the PC amber conversion, full conversion to it. And one important thing, maybe you are not aware of that, but the old lamps were very bad lamps actually, because they were emitting to the sky, but also the span of the light on the ground was very large. With LEDs, generally the optic is a bit better, so not always the case, but can be better, so that it is possible to concentrate the light on the street. And by doing this, you can reduce the power output of the lamp. This is why actually what people, I don't know here, but in Canada, the mayors want to replace all the lights with LEDs because they say that they are more efficient. Actually, it's not true. They are not more efficient than the sodium lamps. Actually, they are less efficient. But given the better optic, okay, you can get the same light level on the street and reduce the power. So in that calculation, we decide to keep the same power. So that means that the reduction we got here is not the real one, because you can easily reduce by a factor of 2 from that level. So if you choose the right LED, you can clearly reduce the light pollution. This is the final conclusion from that kind of experiment. And the other one is that if you look to this island, this specific island, which is inside a few tenths of kilometers, most of the light, about 90% of the light pollution they have is coming from there. This is also very important, because here in Tenerife, we will have, for sure, I know not exactly the results, but I'm sure there will be only the places around the observatory. So we are looking for Guimar, for example, that will probably be one of the main source for the light pollution. Even if, for example, Santa Cruz is a big city, but it's far away. This is why, and in that case also there's some mountains between the two that help to reduce light pollution. Okay, I'll go faster here. Okay, just a few words. I'm almost finished, so it will be shorter than normal. Just a few words to talk about the project here. It's going well, actually, but I work very hard to as I said, to release the new version, but now it's working. I'm very happy with this. And so then I define many zones, and this is the hard part. All circle you see there is a specific zone that will have its own definition of light fixture, spectrum, okay, photometry, obstacle properties, reflectance, etc. So this is interesting to be able to do that, but we have to do it. So there's about 200 zones for that experiment. So I spent maybe three hours with Javier yesterday to try to begin to define what are the type of lamps in each zone. We have done the 2/3 about it, so we have to continue. It is feasible. And myself, I work a bit to check for the obstacles after our meeting. So normally, in a few days, I hope before Friday, I will have all the data to prepare the modeling. So the computer will replace me next week. We have some free time, maybe, hopefully. Okay, and this is another very interesting input that we can try to use. This is an image from the ISS, the International Space Station. You know, the astronauts are taking a nice picture for just not for science, just to have nice pictures actually. And most of the time, if you have, for example, somebody from Spain, we have a lot of images of Spain cities. And sometimes, some month ago, there was a Canadian one. I was so happy. He took some image of Montreal and everything. It was great. So this is, you recognize the Canary Island. But the interesting point with this kind of image is first we have generally a better resolution than the satellite. The satellite is giving us information with a pixel of 750 meters. This kind of image can go down to a few tenths of meters. This is very interesting. This is the first aspect. The second one is that we have the color, because it's a normal, you know, the SLR camera, so you have the red, the green, and the blue information. And we can see it on the picture. And for example, in Gran Canaria, you can see that it's whiter than in other islands, like here and La Palma, it's quite yellow. And we know why, okay? But this is interesting because with that kind of information, we will try also, it's like another part of the project I'm doing here, is we'll try to see, is that possible to use that to replace the kind of expertise that Javier has here on the territory? Because we don't always have some people like him to help us to find the kind of lamp, okay? So if this kind of methodology using simply spaceborne images can replace this hard job we are doing now, can be nice. So at the end of the project, we will compare this data with the one we produce together. Of course, it's not perfect. You can see there are some clouds and some spots of the island, but it's still interesting. And I want to thank two people here in the room, because they are really involved in the protection of the sky. So I'm happy to collaborate with you, actually. Thank you very much. And I think that's all. I hope you have some questions. Thank you very much. Mm. Yeah.
The clouds are. Sorry. Okay. Whoa.
Mhm.
and also as blocking agents.
Exactly.
Stopping the light coming from below.
Mhm.
Is it possible to do it in the model or have to include it in the model?
Now it is not included, unfortunately, but I have to include it for sure. Because in many observatories, this is a problem that happens, especially the one in islands, you know, and most of them are on islands. So it's a key factor, you're right. Mhm. A nice sky. Yeah, this is the point. I talked about before, you know, the clouds overhead, which are like amplifiers. But in the such situation is the opposite. You have like a filter that will remove light. But I have to do it. You're right. It's one thing I should say. I'm especially you know, my PhD was in atmospheric physics, optics, so I know this topic, and it's not easy. Okay, because you know the density of the cloud, the kind of cloud, the thickness of the cloud, the size of the droplets, everything is highly. It is complicated to get this information first, and then the other point is that the scattering in clouds is multiple level scattering. So you have, you know, for the atmosphere, my model, for example, for clear atmosphere, at the beginning, if you go back 15 years ago, I was thinking that probably first order scattering was quite enough to do that kind of job. And after a couple of experiments I made, I realized that I have to compute the second order, and this is not so simple to do. And this is why finally I need supercomputer, because without that, you know, single scattering is very quick to calculate. For clouds, you need maybe I don't know, 10 order of scattering, maybe, I don't know, depend on the cloud density. But it is still very interesting to try to do it, of course, because it is probably the main driver of the sky brightness here. Okay, what I should say is that in the experiment I'm doing here will be the worst case finally. Okay, what happens when there's no clouds, and this is the worst sky you can have. Okay, but the point is knowing that, because we can find some data, some instrument on the mountain. I have one actually myself. So in some day there was no cloud. So we can know this level of light pollution, the real one, and compare to the model for the same conditions. And then we can know, for instance, in that specific case, if I shut down or replace this street in Guimar, for example, what will happen to this level of light pollution? So it will give us a kind of, reduction of the sky brightness, a relative reduction, but still, it's still interesting, no? That's a yeah. For the Hawaii case, we did not compare actually. Okay, but your question is very interesting, but very complex also. The point is that what we found with this kind of theoretical studies is that the light pollution, and if you measure, and I know some people, you are one of them, that measure light pollution, you see a large scatter in the data. The sky brightness is changing with many order of magnitude from one day to the other, and sometimes in the same night. So why? Because there are aerosols that are changing, maybe some clouds, many parameters that the relative humidity of the atmosphere and everything. So this is a complex problem. So the theoretical approach is important because it helps us to understand what are the links between all those complex interaction, physical interaction. But for your question specifically, there are some experiments we made with real comparison with data, and it is very good actually. And there have been recently there will be a new publication in a few weeks about the Montsec region near the northern Spain region and well, Catalonia. And then we already made one experiment, and the agreement was very good between the model. This model, but the previous version, and now what we want to do is to recompute everything with the new one to see if we improve the result. But yeah, it was very similar to what we obtained in the calculation, the theoretical calculation. The point is that what is difficult actually is you have to, if you want to compare a specific observation with the model, you have to get all this specific information about the atmosphere at that moment. And this is the difficult point. But if you are able to do it, we have done for a couple of times. I'm still surprised that the model is very good to fit the data. So, but many times we don't have the information about the atmosphere, so it's hard to compare. This is the point. But it's an important question, because in modeling, often in the past, I remember even in the meteorological modeling, the people were not comparing with data really. Okay, they were including data in the modeling process, but afterward, they were not looking to the agreement between the model and but now it's another period. Now the people are more aware of that. I think it's a good news actually. But for light pollution, yeah. In our case here for the experiment, it's not a big issue, because what we want actually at the end, what we want to know is what will be the most efficient way to reduce. So the exact value is not so important. It's more a kind of a level of reduction, a relative level of reduction that is important. But I can say yeah, it's possible. Alpha magnitude, yeah. Yeah. Just, for example, it's very simple things. First, find where is the most important sources to the sky brightness, okay? And then we can do a conversion to that. It's a theoretical experiment, but okay, let's say in that street, we replace all the lamps by that kind of, for example, PC amber LEDs. We reduce the power to the half. What will happen to the night sky? This is what we will do. So basically, my experiment is in two phases. The first one is to model what is now on the reality. What is as accurate as possible, of course, because I don't have all the information. But so I try to do this now. Then afterward, I will replace everything with PC amber. Okay. Then we will see. I know it's not realistic, but if all the island is replaced with PC amber, what will happen? Then we have a global reduction, for sure. But after, we can, with the contribution map, we can define the reduction for each pixel. By pixel, I mean about 750 meters square pixels. So I will be able to know, where will be the maximum reduction to the night sky on the territory. And this is the idea. And the goal, of course, is to reach maybe half a magnitude. per square arc second. I'm still not sure it's possible. If we shut down, of course we can, but we have to see. Okay, but in many cases, I think it's probably true here, but in our case in Canada, it's very frequent that we see that the people, the cities are lighting maybe between 2 or 4 times too much light level, too many light level, too much, compared to what we really need. Okay, so it's possible to reduce it a lot. There's room for that. Yeah. Yeah, actually, I did not plan to study it, but I can do it. Yeah, it's quite easy. Just have to put one observer there, and because the difficult part is to get the information on the light fixture. So, if we and for La Palma, we already have one precise inventory. So can be a second step, but I work a bit with my PhD student on that. So we maybe will be able to release something in a few months about that. But now the project is more centered around Tenerife. Yeah, of course. Yeah. And we can, it's interesting because we can, with this project, I will have a quite good inventory of Tenerife. So we'll be able to see what will be the reduction in La Palma with this. Yeah? And it's quite easy because I can do it in the next week because, I don't need actually the light, to know the light in La Palma for that. I just see Tenerife as a source of pollution for La Palma and try to see what will happen there. Again, it would be a relative reduction, but still interesting. Well, mhm. That's a good question. My feeling is that, we include this island in the modeling. Okay? So it's not as accurate as we are doing here because it's farther away. But we look into this to know what is the typical, mixture of light they have. And the satellite will see this light. So it will be included in the model. We do not plan to make action plan to modify this lighting there, but we will know the contribution. And one thing I learned for the many years I'm working on that field is that most of the time this kind of light, as you said, it's a big source of light pollution. I agree with you, but this feeling is mostly conditioned by the observation of the horizon. I give you an example. What I want to say is that I'm not convinced that the zenith sky brightness is really affected. Of course it is, but significantly affected by this island. It is, but I think the contribution would be quite small. I will see. It's just a feeling now. I say that because in another case in Canada, in Mont-Mégantic, the observatory nearby my city, there was, during one summer, not one summer, a few weeks, a big accident. A train full of petroleum exploded in a small city, and before the time they took to stop the fire. It took maybe 1 or 2 weeks. And I had an instrument there looking to the zenith. And all the people working at the observatory told me, it was incredible, the light pollution it produced, you know, and of course they were looking to the horizon, okay? And you'd see the dome and everything. But when I looked to the data, I never been able to see it at zenith. You see? So this is why I feel, but it can be wrong. It's just a feeling. I feel that it's not so important. Of course it has an effect, but let's see. We'll see actually with the model. This is the goal of that kind of project. Hmm? Yeah. Mm-hmm. Mm-hmm. I'm sure it is not the best way. The best way, there's a couple of factors, but some are difficult to make an application. But what I found with previous study is that the uplight, the light going up is very important. But not only the one going right up, but the one going near horizon. This kind of light is polluting a lot of sky. Okay, because it goes, yeah. So this part is, for most places, we saw still some that emitted to the sky, but it is quite nice here in Tenerife. So maybe we cannot gain a lot with this. The other point that is very important, I said before, is the obstacles. How the light will be blocked by the obstacles, I mean the buildings, more or less. And this is another good point for Tenerife. If you look to most of the sites, you have narrow streets, and most of the time the light fixtures are lower than the buildings. So, and I found this is a factor of 5 for the reduction of light pollution. Remove the buildings, 5 times more sky brightness. It's very simple. So this is good also. So finally, I should agree with you. The best way here will be just to reduce. Another point is, the light. The total amount of light, of course, if you cut it down by the half, you will have half the sky brightness. But the other point is the color, which is quite important because you know that the blue is scattering more efficiently in the sky. So having light that are more... it's not so simple because, to long distances, the blue is blocked. If you are close to the light fixture, and there's a blue component in the light fixture, you will have a lot of sky brightness. If this light is far away, you will have less. So it's not simple. So, but basically, reducing the light amount is a good way, and maybe be sure that around the observatory, in the nearby sites, nearby village, to remove all the blue lights you can. Okay, and farther away, you can do that, but it's not so as important as for the nearby sites. Yeah. Thank you very much.